Hello, this is Brian Bijoy, and this is my project for this class. I made overheating, ventilation, and air condition energy predictor, or for short HVAC energy predictor. Um, so first thing first, what I did is I imported all my libraries over here. I then went ahead, read the file that was provided in Canvas or in the classroom, and then I renamed all the columns into understandable names or human understandable names such as relative compactness, surface area, wall area, roof area. As you can see in the raw data, it's just labeled as S1, S2, and so on. So it doesn't really make sense. So I renamed those, and then went ahead and deleted the extra column, which is this column. As you can see, it's kind of useless, so I removed it. And I then went ahead and printed the data table, and this part just for me to understand the overall concept of it. Now over here, I went ahead and explore relationships between various columns or concepts. For example, as you can see over here, heating load data and the heating load data and the cooling load data of corresponds to each other. This means like it's a match, and it corresponds highly to each other, as you can see from the heat set. And then I create a new feature called compactness to surface, where where pretty much I divide the column of relative compactness data by the column of the surface area data. And after that, I check the new feature stats statistics, just to see if just to check if the stats were usable in the model or not. And as you can see, this is like the output. Now for the next one, um, for the next session, what I did is I pretty much did this part of the final project, which was build two separate data models. So I did manually, linear regression manually, and what I did is I extract data and target variables from the manual linear progression. So this means this piece of code over here. I then went ahead and defined a function to manually compute my linear regression slope and intercept. So over here, I went ahead and got my slope and intercept for my heating load regression, and I did the same thing for my cooling load regression. I then went ahead and given each of them a linear slope. As you can see, the linear slope is that, and I went ahead and plotted in a graph. Now this is the graph that was outputted, and as you can see, it's pretty darn good, accurate, I guess. Now, on the next session, um, I went beyond linear and tried polynomial regression with a new feature. So what I did over here was um, let me see, prepared features, relative contact, compactness of surface values. Um, so in this section, I use polynomial regression to better capture non-linear relationship between features and heating load. I started by selecting two features, so relative compactness and compactness to surface. I scaled them over here, and then use polynomial feature to create squared and interaction terms. Polynomial feature over here, square interaction terms. Um, After training, so this is where I train my model. So after training, linear regression model on this polynomial feature, I compared the predictions against the actual heating load, and as shown, and then I went ahead, plotted the graph, and as shown in the script flow, most points are close to the red diagonal line over here, and meaning that the model did a good job approximating the heating load. Once again, what I did over here, so once again, I prepare features for polynomial regression. I scale features to zero mean and univariance for better model training. I prepare features for polynomial regression over here. I scale feature to zero mean and univariance for better model training. I generate polynomial features, odd square interaction terms over here. And then I initialize and train linear regression models on polynomial features for heating load. I then predict heating load using the polynomial regression model, which is over here. And then I actually plot the actual versus predicted. And as you can see over here, uh, it's a good approximation once again. Now, in the next session, or the next cell code, so I checked how good my models actually are. To compare the performance of my models, I calculated two common error metrics, mean absolute error, MAE, and root mean squared error, RMSE. This part calculates the MAE and RMSE for the manual linear regression model. Um, so this part, and then MAE tells us how far um, on average the prediction are from the actual values. RMSE gives us a similar idea but penalizes larger errors more, which is helpful for spotting big misses. Then I do the same thing over here for the polynomial regression model, which includes squared and interaction features. Then I will go ahead and print a statement display the final result for both models. So pretty much I print the result, and as predicted over here, polynomial does better, but my regression still holds its own. As you can see on the output, um, polynomial model made smaller consistent predictions, likely because it could capture more complex relationship in the data that basic line couldn't. Now on the next session, in this section, I trained two random forest models, one for predicting heating load and one for cooling load. Using all available building features, including the engineered one, over here, I first dropped the target column and kept the rest as input features. I scaled the feature using standard scaler so the model treats all variables fairly, especially those with different ranges. So that's what I did over here. So I calibrated my data pretty much. I then trained random forest regressors. That means that I trained two random forest models, one for heating, one for cooling, and random forest is it's a good machine learning algorithm that works well for these kind of predictions. Now, a cool feature about um, random forest is I can rank how important each input is for making predictions, and that's what I did over here. So, and then went ahead and I plotted my graph. As you can see, surface area and roof area are large contributors. Now, for the next code session, what I did was pretty much this part of the final project where I inputted where after training my model, I actually went ahead and inputted different cells into my model, as you can see over here. Um, I could have probably made another CSV file, but I went ahead and just do it manually. Now, uh, after After I trained them, check the training data over here. I scale the new input so it matches the model expectations. Over here, I then use my trained random forest model to predict both heating and cooling loads. And I finally over here I finally added those prediction back to the table to see the results. This gives us a quick and easy way to estimate HVAC for any building design just by entering its data pretty much.